In the last video I discussed resonance as it pertains to hybridization, and the reason we begin with resonance is with hybridization, with geometry, we're asking how the electrons around an atom are sitting in space, how they are shaped, or how to what angle they come from the given nucleus, and that eventually, as we put that all together from atom to atom, can tell us the shape of a molecule, which is pertinent and telling of its chemistry in many contexts. Okay, and so to understand how electrons are sitting in space for a given atom, we need to see if they can move, if they're shared, or if they're owned. Okay, another way to say that is if they're shared or if they're delocalized, and if they're owned or localized to that atom. Okay, and there are three different examples of resonance that I showed in the video. The first one being just a benzene or phenyl ring, or one very much like it. And really what you're looking for is an even number of atoms in the given ring and the pattern of double to single to double to single bonds and so on. Okay, and when you have that, you essentially get the double bonds to just have a perfect rotation around the ring, so they're all in a new position. Everything that was a double bond is now a single, and vice versa. Okay, showing here, you can also get this oxygen to resonate into the ring, and it's something we'll look more at in a moment, but I just want to point out that yes, you can have this oxygen resonate down, form a double bond, and maybe push these electrons up to one of the carbons. Okay, we'll touch more on that in a moment. In the second example, I discussed the open shell. Okay, and all you're looking for is any atom that doesn't have a full octet, doesn't have 8 electrons in its shell, right? Here we know that this carbon is open shell, and the reason is given that it's neutral, we're told that it has 4 atoms that you may want to, that you could very well consider as owned, and 6 electrons, so I'm sorry, 4 electrons that it may be considered as owned, and 6 total electrons in its shell. When we're referring to owned, we would say it owns any lone pair, and it shares one of 2 electrons in any bond. An easier way to calculate this is count the sticks and dots around the atom. So we have 1, 2, 3, 4. Okay, and carbon, which this is a lot of gen chem that I won't go too deep into, but carbon likes to have 4 electrons to be owned, and here it does have 4, and so its net formal charge is 0. Okay, so its net charge is 0. It's implying that it has no hydrogen in this structure. It just has the 2 bonds and the lone pair, so that totals at 2, 4, 6 electrons. And when you have that, you have an open shell. And when you have an open shell, any adjacent atom with a lone pair is able to resonate down, form a bond, and therefore fill your shell. And we would consider then one of the pairs of electrons on this oxygen to be able to move, to be delocalized, which we'll touch on more in the next video with hybridization. Okay. Right now we just want to understand how to recognize when electrons can move, when they can resonate away, so that we can use that to understand hybridization moving forward. The third and final and slightly more involved example is electron bouncing, so to speak. And we have 3 models where we can consider any atom with a lone pair in the A position. Okay, so you look at any molecule, and if any atom in it has a lone pair, you pretend or consider it in the A position and see if the other 2 of 3 criteria are met. The first one being it just needs to have a lone pair on that given atom. The second criteria is that atom needs to have a single or a double bond with any adjacent atom. Here we see single, double, and single. Okay, and from there, from that adjacent atom, here it's consistently carbon. That carbon, or the second atom, needs to have a double or triple bond with yet another atom. If those 3 criteria are met, then you can have resonance. You can have the lone pair on the A position atom form a bond and push one of the double or triple bonds up, okay, to the 3rd atom in this entire model. Okay, so applying this to some of the molecules, starting up here, we can consider this nitrogen. It has a lone pair. can say let's consider one of the two lone pairs. Okay, you can only consider one at a time, and it has a single or double, has a double here, and then double or triple has a double yet again. Okay, so that means 3 criteria are met. We can follow the same pattern of form a bond and push a bond up as a lone pair. Okay, and so also notice that our charges move. We have the negative nitrogen is now neutral. Its lone pair has become a bond. Okay, so you can think of that in very simplistic form as it has less negative things around it. Electrons are negative. They are not right on the atom. Instead, they're being shared between two. So this atom, this nitrogen in this resonance contributor does not have as much negativity around it, or more simply put, it goes from a -1 charge to neutral. And this carbon has just the opposite. It was sharing these electrons, but in this resonance contributor, it has them local to itself, to its nucleus, and thus it bears a -1 formal charge. And then we see the pattern continue. We have lone pair. We consider this carbon in the A position. We have single or double, so single, and then double or triple, so double. I keep saying it that way because it helps you somewhat remember. If you just say, okay, atom with a lone pair, we need single or double or triple. Okay, with repetition, it may help you remember it. If not, then it may just be annoying, and that's fine. I do want to point out that if we look at this oxygen, it does have a lone pair. We have a double bond, but we do not have a double or triple on the next relationship. Okay, so both of these pairs of electrons are localized to this oxygen. I also would like to point out that while this nitrogen has 2 lone pairs, as I mentioned, we have to consider one at a time. So to do so, we actually resonate one pair down and look at the result before we're able to consider, does the second lone pair resonate? And again, we just look at the model, one of the 3, and if it fits, then it does. If it doesn't, then the lone pair is local to the nitrogen. And so we have a lone pair. Single or double, which is not met, we have a triple bond here, and then double or triple, which is also not met. So 2 of the 3 criteria are not met. We would say this lone pair, or rather one of the 2 lone pairs on this nitrogen is localized and unable to move, and the other of 2 pairs is able to move. It's delocalized, it can resonate. Okay. 2 more examples down here. I just want to show where you're able to skip steps. Okay, these are 3 of many resonance contributors. Okay, there's a few of them that are not shown. That does not mean that they are invalid. It just means skipping a few steps, showing just the contributors that put a negative charge on an oxygen. Okay, so where we would normally resonate down, lone pair, single bond, push this bond up to the carbon, end up with a negative charge and everything, or a smiley face. And then we could say, okay, lone pair, single, and double, we could push those down again, push them up to this carbon, lone pair, negative charge, and once again, lone pair, single bond forming a double bond, pushing up to put a lone pair on the oxygen. Or we could skip all of these steps. And how to recognize this is that you could consider this double bond if you know it's the bond that will be pushed up as a lone pair on this carbon or on whichever atom is in this position. If we consider this the A, this the central, and this the second atom. Okay, if we know this pi bond is going to end up on this carbon, we can just consider it as the lone pair on our A position and whatever atom, here the carbon, that it would end up on as our second round A position. And so if this is our A and this is our lone pair, we have single and then double. So we could resonate it down, push it up, and then once again we could push it, that lone pair from this carbon down and push this double bond up. So that's the very long way of saying all of that. We could also kind of piggyback from our first example here, where we see double, single, double, single, double, single, and these pi bonds just bounce and push each other along. The same idea applies with this skipping step method, so to speak. The electrons come down and we see that we have double, single, double, single, double. Now, to point out that eventually electrons need to end up on an atom. Okay? You've reached the end point of this skipping step method when the electrons have resulted or ended up on any atom. Here, this oxygen. Okay? And we could also have, let's use green. We could have also just gone this way. Here we go. And push the electrons up, which would have skipped straight to this option. Or we could very well just show it here, the skipping method. Okay, we have double, single, double, so we know we can push them. And we have double, single, double, so we can just keep going. Could actually skip here, and this double bond that we originally formed would end up back up there, and we would result in this contributor here. Okay. Now, it's a little unorthodox to do it in that way. It's not something that's highly recommended, but I do just want to emphasize and show the electron bouncing. Okay. There is one exception to this rule, and the exception itself has a rule. It is that you cannot have an sp atom in a ring. And all that really means is an atom with only bonding to only two things and no lone pairs, no third atom to which it's bound. And if it's only bound to two things and it's in a ring, we would consider that possibility as invalid. The reason being, and we'll see this more when we discuss geometry and hybridization, is, for instance, this nitrogen, as we look deeper into the chemistry, should actually be linear if it's only bound to two things. So here, carbons, sorry, that's a carbon. Okay, and this ring would be too constrained on the nitrogen. It would have to try to torque this this bond that would otherwise be desired to be linear and straight. You'd have to torque them in to fit in this pentagon. Okay, and so we would just say it's too high energy. It's not a possible structure, not a possible resonance contributor, and therefore this lone pair is actually localized to that nitrogen. It's incapable of resonating. Okay, and to just draw on the examples that we had, we have A position because it has a lone pair, single, and then double. So I can push, okay, and push them right up to there. That would draw us to this contributor. Or it could have skipped the step. Let's go with green again. In which case it would have come down, skipped over, and pushed the electrons up to the oxygen. And that gives us and leads us to this bottom contributor here. Okay, so in the next video, I will go over how we use this this information, these strategies, to understand the hybridization of any given atom in a molecule and its geometry, polarity, and so on.